Okay, engineering students, welcome to this session of looking at physical properties of organic compounds. These are in the soft copy of the lecture notes, which you have. Uh, but there is something that I need to just mention because it cuts across the functional groups that I'm going to be talking about. In this case, I want to say here we've got uh, the first functional group which we are talking about, like alkanes, which we know, which are saying it has carbon hydrogen single bonds and in principle does not have a functional group. So an alkene has got a carbon-carbon double bond, and an alkyne has got a carbon-carbon triple bond. So what you're going to see is, if I've got like the structure of an alkane, for example, uh, there's that alkane. Maybe I've got another one. In this case, I'm going to, because of the stretching, I'm going to use this format here. And then okay, so I'm going to put okay, I'm going to put a similar one here. Okay, that one. And then I say this is equivalent to let me say 1, 2, and then this other one is 1, 2. Okay, that one. So it means that if you're going to have another one, you're going to have it something like this. You've got another molecule like that. So that in this case, 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. And then I want to look at the other one, in which, in this case, if I've got so this is equivalent to, so in this case, if you're going to have many of these, okay, what can you see there? This is an alkane, like this one, 1, 2, 3, 4, 5, 5 carbon atoms, which I'm saying you've got one molecule with 5 carbon atoms, and then I've got another one close by. So the predominant intermolecular force of attraction in alkanes and also alkanes and alkynes is called van der Waals force, or London dispersion forces. Yeah. So these are weak intermolecular forces between one molecule and another one. So because of these weak intermolecular forces, you're going to see that the melting point and the boiling point of alkanes, alkenes, and alkynes is going to be very, very, very low. So you're going to see from the tables as provided in the soft copy that, for example, you're going to see like the one for methane, for example, or maybe something like ethene or ethine. You're going to see they're going to be very low, negative, over negative 100 degrees Celsius and below. They're going to have a very low melting and boiling point. But why did I draw this these structures like this? Yeah? You're going to see that this alkane 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 exists in a zigzag manner. And if you're going to put many of them together, you're going to see that if they're going to be linear structures, I can pack many of them within a certain unit volume. Many of these can pack together. Similarly, if I'm going to have like having a trans double bond for an alkene, yeah, they can pack quite well. But if you're going to have a cis, you can only get probably like 3 of them which can pack in a place, which are by 5 or 6 can pack, like if you've got trans, and probably something like a linear chain of an alkane. But then there's something else which I want to introduce here. What if I've got a structure like this one of 1, 2, 3, 4, 5. What I'm going to say that I want to put in another one here, and then probably just look at this volume here. If I'm going to add in branches, the branch like this one has got a methyl group and a methyl group here, is going to prevent compact packing between one molecule and another one. So the forces of attraction between the molecules is going to be much less than if there are no branches. So it means that the more the branches in the molecule, the less the packing. Yeah. So if there will be the less the packing, then that will mean there will be less intermolecular forces, and that will lead to much lower melting and boiling point. What does that tell you? If you have an isomer which does not have branches, and you've got another isomer which has got branches, then the one which has got branches is going to have a comparably lower melting and boiling point than the one which does not have the branches. Yeah. So the more the branches, the less the packing, and that results to less intermolecular forces, and that will lead to lower melting and boiling point. Is that okay? Yeah. So that is the variation which you're going to get, but you're going to see this point is going to become clear when you'll be dealing with fuels. Yeah. Or maybe I can mention before we really come to that, when we'll be dealing with fuels like the petrol, you're going to see that there is an isomer of octane. Octane itself burns very poorly in a gasoline engine or in a petrol engine. But if you're going to get it into an isomer called 2,2,4 trimethyl pentane, but it's trimethyl, it means that it has 3 methyl groups, and therefore the total number of carbon atoms is 8, and therefore it's true to be an octane. But because of the way it's branched, it vaporizes easily, and therefore it burns much more efficiently than the octane, and therefore it is said to have an octane rating of 100, as opposed to the normal octane, like even some other one closer to it, which do not have branches. But that one we're going to mention under the fuels later in the course. So the branching causes the boiling point to be low, because there is lower intermolecular forces. Yeah. So this argument applies for alkanes, alkenes, and alkynes. These are just hydrocarbons. They've got carbon and hydrogen, and as you know, there is very little electronegativity difference between carbon and hydrogen. One has got an electronegativity of 2.1, and the other one is 2.5. So very little electronegativity difference of 0.4. We say that if you have an electronegativity difference from 0.5 to about 1.9, then that bond will be said to be polar covalent. So less than 0.5, then the bond will essentially be non-polar. Yeah. So alkanes, alkenes, and alkynes are essentially non-polar. Yeah. Uh, so in this course, we're not going to be dealing with a lot of chemical reactions. You're not going to be dealing with a lot of chemical reactions, but when we'll be dealing with alkanes, alkenes, especially alkanes, you're going to see that the most common chemical reactions they undergo is combustion, and I'm going to see this one under under fuels, whereby we'll be looking at how, if you're going to have an alkane, like maybe like what's a 1, 2, 3, 4, 5, like this one, each containing 5 carbon atoms, you're going to say it can burn in oxygen to produce carbon dioxide plus water. If you have X grams of your alkane, how many it can be able to predict from the molecular formula how many grams of carbon dioxide will be produced, and how many grams of also water will be released, and also how much oxygen will be required for the combustion. All that we're going to be relating to the to the uh, to the molecular formula for the alkane, and then we see with the oxygen, and then we see from the balanced equation that this alkane is going to require this number of moles of oxygen, and is going to produce this moles of carbon dioxide plus this moles of water. And then from there, just from that one information, simple information about the molecular weight of the alkane which you're burning, you can get all the things, all the variables that you require. Yeah. Yeah. Now in this case, it applies like the one for the combustion. It applies for complete combustion, whereby you are burning in excess oxygen, and therefore you're going to be producing what? Carbon dioxide plus water. But if there is incomplete combustion, then you know, like for organic matter, you're going to produce what? Carbon monoxide, and it will be carbon monoxide plus oxygen, and the equation will become a bit complicated. But as for now, we're only dealing with complete combustion, and we'll be forming carbon dioxide plus water. So I think with that, you'll be able to look at more about the tables which you have in the soft copy of the notes, to be able to show you the variation of the melting point and boiling point of alkanes, alkenes, and alkynes, and to know the cause for the variation of the melting point and and the boiling point. Yeah. Yeah. So I think we're going to take a short break. Then I think we'll look at. Okay. By the way, this argument may also apply for benzene compounds, though benzene has got something like 6 carbon atoms, and therefore it's going to be a little bit what? It's going to be a little bit more dense. It's going to have a higher molecular mass, and the higher the molecular mass, especially if you're dealing with 6 carbon atoms, then it will not be a gas, but it will be a liquid at room temperature. So benzene and also alkanes, alkenes, alkynes, which may have something like 5 or 6 carbon atoms, they are going to be what? They are going to be liquids at room temperature, for example. But something which has got 1, 2, 3, probably 4 carbon atoms, like for butane, it's going to be a gas at room temperature. But you're going to see that for something like butane, which is an alkane of 4 carbon atoms, you can be able to compress it, and it's going to become a liquid under pressure. It's called liquefied petroleum gas, LPG. This one has got to do with something like critical temperature and pressure, of which uh, there are those curves for the physical chemistry, which tells you that if you're going to achieve a certain pressure and temperature for some moderate molecule, not tiny ones like methane, you can be able to bring them sufficiently closer and under that pressure to be able to make them liquefy. It's called the supercritical temperature and pressure. But that one we're not going to be discussing in this course. But without those pressure and the temperature which are required to liquefy, um, the first four alkanes are going to be what? Are going to be gases, yeah? So, so the more as you're going to be increasing the molecular weight, they're going to become, okay, they're going to be liquids, and then beyond a certain level, then they're going to become solid. Like in this case, if they're going to be solid, they're going to become waxes, yeah? Wax like the one in candle. It means that like maybe 20 carbon atoms. It will be a white wax, something like that, yeah? But once again, I would let you to look at the notes so that I don't give all that information about the various uh, hydrocarbons and their melting points and the boiling points. You have the notes and also the reference documents. They will be able to give you the various information that you require. So I think for now, let me stop on that one for this first three. I mentioned this includes also benzene, benzene compounds, which are in this case they're called aromatic compounds, provided they do not have uh, functional groups such as the halogens and something like and uh, and ether and the rest. In this case, you're talking about a benzene. It has a branch, a substituent like what? Like a methane, a methyl group, an ethyl, and isopropyl. All those are alkyl hydrocarbons. So in this case, the predominant intermolecular force will be van der Waals force, or the London dispersion forces, as they are called. Yeah, yeah. So those are that means that 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 the melting and the boiling points will be fairly low compared to the molecules which have more stronger intermolecular force, which you're going to see like the dipole and the hydrogen bonds. So you're going to see for something like water, or maybe something like alcohol and maybe carboxylic acid. You're going to see that you can have a small molecule with maybe even one carbon atom, but the melting point and the boiling point is very high because of the intermolecular forces. But for these other ones which you're talking about, alkanes, alkenes, alkynes, and benzene compounds, the melting and the boiling point is fairly low because of the intermolecular forces that exist in those structure. And once again, the more the branching, the less the packing within a unit volume, and that means there will be less intermolecular forces, and that will lead to lower melting and boiling point compared to the isomer, which is not branched. So that is the take-home message to remember regarding this four functional groups: alkanes, alkenes, alkynes, and also the benzene or the aromatic compounds, as they are called. Okay, so you're going to stop there for this first session, and then we'll look at the other functional groups shortly. I hope you've enjoyed. Yeah, thank you.